Our first speaker today, Adam Cutler, is the chair of our Lubrication Working Committee, and he's been surrounded by lubrication analysis since birth. He's the founder of Analysis Laboratories in the UK. He also operates learnoilanalysis.com, which is a platform that provides free online training. Adam will also be presenting in person at the BINDT conference from the 9th to the 11th of June in York this year. Adam will provide us today an insight on what harm the wrong oil can do in application. This is a problem we see very frequently. Thank you for joining us, Adam. Are you okay to share your presentation and then I can hand over?
Okay, thank you very much, Jade, and thank you for the introduction there. So today I'm going to talk about what harm can the wrong oil do. So first of all, why the topic? So if we think about oil suppliers or lube suppliers globally, you may recognize names such as Shell, ExxonMobil, BP Castrol, Total, Valvoline, Fuchs, Chevron. All these brands you recognize throughout the industry, and they all have their own market share. And this is some estimates of market share based on the litres of oils they sell each year. But this is based on litres of oils, but this may not be the best way to measure it. And so in terms of actual customer perception, this information is wrong. So the most popular oil in the world sold right now is actually unknown. So most of all the oils, in fact, more than all the others combined, people do not know what actual oil they're using. So many people don't know what oil is in their car or the machinery. And so if we expand that a little more on here, we have what are the most common brands people use. Unknown is number one. Then there's I think it's, so that could be I think it's Shell, I think it's Castrol, I think it's synthetic, or it could be a mix of. So it's a mix of one, I topped it up with another. And so not knowing the right oil is actually a real problem in the industry. So does the type of lubricant actually matter? So that question, the answer there is actually not right. It's wrong because we need to understand how lubricants work and why, and that will help us understand things. So let's talk a little bit about the function of a lubricant. So the most obvious one people think of is it reduces friction. So separating the surfaces and allowing the components to move past each other. We also think of it as preventing wear. Obviously, you don't want things to wear. It can also dissipate heat. We also want it to prevent corrosion. So if we get water into the system, we want it to remove it and prevent it from causing corrosion to components. It can also clean. Now, this can be through additives, so detergents, but also physically just transporting the oil to a filter that does the cleanup job. As well, an overlooked feature is the ability to seal. So if you take an engine, for instance, the piston rings are often thought as sealing, but it's actually that little small tiny layer of oil beyond the piston rings between that and the cylinder liner that does the final seal to prevent leakage of combustion gases. And then anyone who's in the hydraulic industry, there will be the ability to transmit power and dampen shock as well. So let's start off with the first one, so reducing friction, which is the one that most people think of when you think about what's the function of a lubricant. So what affects friction? Well, there's a few factors, but one of the key ones is the viscosity. So viscosity is resistance to flow, but in layman's terms, it's how thick an oil is. So we can see here, we've got on the left-hand side, we've got a very thin oil, and on the right-hand side, a very thick oil. Obviously, it has more resistance pouring from one container to the other, so pours more slowly into one container than the other when it's a thicker oil. So how do we measure viscosity? So there's several ways of measuring viscosity, but a common way of doing it is kinematic viscosity, which you have a oil-filled bath that we, under gravity, drop the oil down one end of a viscometer tube, and it then reaches the final point at the bottom under controlled temperature, and then we know by the time it takes to get from one point to the other how thick the oil is. So if we just take this bath here, so on the left-hand side, I've got three tubes on here I've highlighted. I'll just highlight for you on screen. You can see I've highlighted those there. And if we just put some oil down each of these tubes now, so we're just going to put some down each of the tubes, and we can see that this one on the right-hand side is actually hit the bottom before the first one, although that started first, has actually reached it and it's now finished. Now, the reason for that is a much thicker oil, has more resistance to flow, and so takes longer despite starting earlier. So what happens when an oil is too thick? So if we think in something like an engine, for instance, obviously if you think you're trying to move components through a very viscous oil, that's going to give a lot of resistance and a lot of drag. That's going to lead to increased pump load, and it's also going to reduce to lower fuel efficiency. Whereas a thinner oil is going to have less drag, and so it's going to be easier to flow, and so it's going to be easier to pump it around, and so you get better fuel economy. And that's why a lot of modern formulation oils tend to be thinner, because it gives less drag and gives you a better fuel economy as a result. But can it be too thin? So this actually brings us into our next area, which is preventing wear. So a too thick an oil, as I highlighted before, if you've got something that's too thick, you have a high energy consumption, but you get a really good film thickness. In contrast, if something is too thin, you get a better fuel economy, at least at the start, but you get more risk of metal-to-metal contact. So you don't want an oil that is too thick or too thin. You want this Goldilocks zone of something just right that is thick enough to give surface separation, but not too thick that's going to lead to increased drag and increased energy consumption. So what happens to the film thickness? So if we think we've just got a brand new component now, and we just take a plain bearing, for instance, as the surfaces move past one another, we think of them as being perfectly smooth, and they look very perfectly smooth to naked eye. But at a microscopic level, they have these surface imperfections, and we call these asperities. And these give little troughs and valleys as the surfaces move past one another. And you can imagine these will bump into each other as we move them. So as we see here, they're moving past each other, and we get these materials break off. And these then deposit and react with lubricant additives and form what's called a shear mix layer or boundary lubrication. And what happens is that under normal circumstances, you have the full fluid thickness, so the oil is separating the components. But under like reasonable load, but not overloading, you can have it where the actual surface actually comes into contact just from the additives itself. But if you take this too far, you can get metal-to-metal contact, which is abnormal wear. So the boundary lubrication is typically normal wear, but if you overwhelm that, you get abnormal wear. So on here, if you have a look, if you get to the abnormal wear from metal-to-metal contact, you lead to sliding wear. And you can see on this particle here, we've got almost like a grain to the material. These are called striations, and these are significant in a sliding wear contact like I just showed. So if we have our normal system here with a full fluid thickness, and if we have one which has got a too thin a film thickness, we can have boundary lubrication touching and then going beyond and actually breaking that and getting to metal contact. And this leads to increased wear in the system. So I've already pointed out that viscosity affects the first two functions of a lubricant. And that's because viscosity is the most important property of a lubricant. So much so, I'm going to talk about it again now. So we talk about dissipating heat. And we talk about viscosity index. So I described earlier when we talked about viscosity that we have a temperature controlled bath. Now that's because that all oils thin with increasing temperature. So if we just take a classic thing, I always think of this when I'm cooking. So if I've got a cold pan here and I put a blob of oil in it, when I heat it, that oil spreads out across the pan. That's because it is reduced in viscosity and so has less resistance to flow. So it flows around the pan much easier. So we measure this change over temperature in something called a viscosity index, and that looks at the temperature at 40 degrees Celsius and 100 degrees Celsius. Now, if we just take this example system here where we've got an operating temperature of, say, 95 degrees Celsius. Now, this could be an engine, for instance. All the oils give the exact same target at operating temperature, so they're equally as good as far as the film thickness at operating temperature. But if we to take this oil and extrapolate off here, it's going to be very thick at cold temperatures, whereas this one's going to be very stable. This is technically the perfect viscosity index. It's like infinite here, but this is unrealistic. You'll never get this, but you try and get as close to this as possible. So who will this suit? So someone who's working in these cold conditions here, they're trying to start the engine. They want this to be as close to this perfect line here because they want it to not get too thick when they're at colder temperatures. But this doesn't necessarily suit everyone. So if we take an oil that is being used to transfer heat away from a component, you want actually that as soon as it heats up to get very thin very fast so it can flow away to allow fresh cool oil to go and cool down the component. So a very, very low viscosity index would be desirable in those circumstances as opposed to the high viscosity index when you want good temperature stability. So another thing you may be thinking of, isn't the oil being oxidized from the heat here? So this is where we come on to prevention of rust and corrosion and oxidation. So all lubricants contain anti-rust and antioxidant additives, or called an R&O additive package. So all oils contain these in their lubricant formulations. It's part of the basic oil formulation. So you could argue, are all oils suitable for corrosion prevention? Well, it depends. So if we take something like an ester, so there's several types of esters, but some of the key properties some of the esters have, something like a phosphate ester has good fire resistance. Something like a biodegradable ester, obviously by the name, they are biodegradable, so have good environmental credentials, but they're also good solvents, and they tend to have good, very high viscosity indexes as well. So all these could be desirable properties. And they'll all have rust and antioxidant additives in their additive package, but esters are made from acid plus alcohol equals ester plus water. But we can reverse that reaction. So if we add the water, we can split the ester back into an acid, and that acid can cause corrosion. So in this case here, a wet environment is not the ideal circumstances to use an ester-based lubricant. So we can see here, we have a test specimen, and normally we do this test over 4 or 24 hours, depending on the client's requirements. This is after 40 minutes of testing, and this is not the anti-rust corrosion additive being spent. This is actually the oil has been split because we mix oil and water together to see how well it prevents corrosion. But the water had split the oil so it split the ester into acids, and this was causing corrosion. So is it just the base oil and antioxidants that's causing issues? Well, no, it can also be other additives as well. So a common one is EP, extreme pressure oil additive, which is used in many, many gear oils and gives that sulfury, unpleasant smell you can smell in gear oils. Now, these are really good for wear protection, but one of the disadvantages is that EP can attack copper components. And this can eventually, over time, lead to copper sulfide formation and eventually, over a very long period of time, tarnishing and dissolving of components in a gearbox over time. And the way we measure this in the lab is we do a copper corrosion. So we simulate that environment and we take a copper test strip and see how much tarnishes. You can see this specimen here is actually not looking too healthy compared to, on the left-hand side, what a nice, fresh, healthy specimen should look like. So we can also, as well, the function of a lubricant includes cleaning and transporting the debris. So the thing I want you to get from this is that the dirty oil is a wrong oil. So if the oil is dirty, this is not the right oil for you. Now, I'm not going to go too much into this because following on later on, the last presentation will be Dimitri, so you've got something to look forward there to hear more about contamination effects. So stay tuned for that presentation. Lubricants are also required to seal, as I mentioned before. So a common issue you have is when switching from one brand or one type of oil to another in large lubricated systems, you can lead to shrinkage or swelling of seals, which lead to them not setting right in the housing and leading to small leaks throughout the system. And this is one of the things when you're switching in very large oil systems and large lubrication systems is to actually check for seal compatibility. So some of the ways you can do this is you can measure an aniline point. So you can measure the inherently the aromaticity of the products, and this will give an indication of how well and how compatible the oils will be. You can also do direct specimen testing. So you can take one of the seals and you can take the old oil and you can take the new oil and see how the swell effects would be on that on that specimen. So we can see here we've got two equally sized specimens here. Now this one you can see is very slightly bigger than this one at the bottom. So you can see this is actually swollen a little bit more. Now, if we wanted it to be like this one, they would have gaps here because we're not getting enough swell. Or if it was vice versa, we wanted to have this one, and this is what the alternative product is, it could overswell and lead to, again, disruption of the seal. We also want to, as well, dampen shock and transmit power. So if any of you have ever put your foot on the brakes and it's not gone too well, this can be down to air in the brakes. And so obviously that's a safety issue, but this also happens in anything in hydraulic power. So air obviously is compressible. And so foam in a lubricant or high air release tendency to a lubricant can all lead to uncontrolled movements, can lead to safety issues because it's uncontrolled, but can also over time, because air is compressible, that air gets superheated. And so over time, that heated air will burn the oil around it and form little soot particles. And so you can actually get a process called microdieseling. So the oil actually over time starts to soot. So in conclusion, what I would like to get from this is that oil analysis assesses all these parameters and looks at all of these aspects of have you got the right oil for the right purpose. So it'll look at viscosity, looking have you got the right film thickness. It'll look at the elemental analysis to see are you getting wear and have you got the right additive pack there. It'll look at infrared to see you've got the right type of lubricant. It'll look at viscosity index to look have you got the oil is working over different temperature ranges at the correct amount. It will also measure how spent a lubricant additive is and how much resistance a new lubricant will have to depletion. It'll also look at the corrosion and air handling and water handling properties and all these properties, and all this can be found out from a single oil sample. So I'm not going to answer any questions now. This will be all done at the end in the panel session. But I'd just like to remind everyone that there's no silly questions. It's better to ask before doing and to put these into the webinar chat, and we'll all answer at the end. So I'm just going to hand back to Jade now, and thank you very much for listening.